All right, now that we've seen the theory around algorithm analysis, let's apply it to iterative algorithms, and let's see how iterative algorithms should be analyzed in general. So we'll find that to analyze iterative algorithms, we need to find the critical instruction. That means that we need to find the instruction that is repeated as often as any other instruction, or that is repeated the most. If we have a series of loops nested in each other, then any instruction that appears in here would be valid. But if we have, for example, parallel loops, we would need to find the one that is the longest and then add them up by performing the maximum of both. And probably the instruction that appears here that has the highest cost, either by itself or by multiplying with the 4, will be the one that will be the highest one. So let's see a couple of versions. First, let's see a simple traversal algorithm. So let's assume that the processing that we do here is something that is constant. So for example, a plus b, or sum plus equals value, or something of the sort, right? And this is executed the length of the vector through the length of the vector. So n would be the length of the vector, as we can see here. We can see no significant instances because every time that we run this, it's going to perform exactly the same regardless of the input we give it, because we assume that this is constant. And thus, if we have a constant value repeated n times, we can express it as such. And the result is that we are executed something n times, and thus we obtain a linear result. If instead of a traversal, we get a search, for example, a sequential search algorithm, and we're looking to find a value in a list, in this case, we need to differentiate between multiple instances. So imagine if we had a list from 1 up to 1,000, and we were looking for a random value. It's not the same thing to look for value 1, which would be found immediately, than to look for value, I don't know, -5, which would never be found, or to look for value 532, which would be found halfway around the list. So for the best case, we can see that if we started here with the first value and we were searching for the first value in the list, we would execute this, and then we would execute the for loop, perform this comparison, and finally return. Thus, we have executed only one instruction. Here we would consider the critical instruction. Be very careful. We shouldn't consider the return. This is not the critical instruction. Why? Because most of the time this would be false, and thus this will never be executed. And thus this is not executed as often as other instructions, for example, the if. This is not the valid critical instruction, and you should never pick it. If you have an if conditional, its inner statements can never be the critical instruction. Instead, the critical instruction can be the comparison here. In the general case, we would go through this for the number of times that this list has. So we could say that the size is equal to the length of the list. And thus we would have a similar case as with the last one, in which we would execute this every time. We would never find it, end up returning -1. And thus we would have a sum from I equals 0 to the length of the list, so n minus 1. And each time we would execute a constant operation, which would be the equality, so 1. And this is n. And thus we have a linear cost for the worst case. But what happens in the average case? So to study the average case, we need to think about what happens in all other cases. So what happens if we're looking for a random number that appears in the list? In our list from 1 to 1,000, we know that if the value doesn't appear, we will perform 1,000 operations. And if the value is the first one, we'll perform around one operation. But what happens in all of the cases? Well, we can model for that, as in we can imagine that, okay, let's see what the search would be for 1. Let's see what the search could be for 2. Let's see what the search could be for 3, etc., etc., etc. And then with that, we could find this list of probabilities. This means that divided by 1/n, because each of these has a 1/n chance of appearing, this would be the costs. Then this would be converted into this symmetry, and we could solve it with this transformation. This symmetry would be converted into this fraction. And if we multiply these two terms, we obtain a linear result, and thus our average time is linear. But let's say you wanted to also imagine what happens if half the time the element we're looking for is not there. Then we can say, okay, what's the average time for when it is there, and what's the average time for when it isn't? And then we can compute both and see that the result is still linear. So a sequential search algorithm has a best case of 1 and a worst case of n, and an average case also of n.